Hello, this is the lecture for section 3.7, rational functions. Let's begin with a definition. What is a rational function? Well, most easily put, it's simply a fraction where the numerator is a polynomial and the denominator is a polynomial. Here's a form that we can apply or a standard form for polynomials. If we have the numerator called p of x, the denominator q of x, it might look something like that. All right, rational functions are interesting. There's some characteristics that are particular to rational functions called asymptotes. So let's take a look at a definition for asymptotes. We can have both vertical and horizontal asymptotes. A vertical asymptote is kind of an invisible line that the graph would never cross over. So if I were to draw an example of a vertical asymptote, some particular function, it might look something like this. Okay, the vertical asymptote would be this dotted line. And if that's a 2 right there, we would call that vertical asymptote x equals 2. All right, here's a more formal definition. A vertical line x equals a, some value, where the graph tends toward or approaches positive or negative infinity as the inputs approach that value a, right? Or we might say in symbols, as x approaches a, f of x approaches positive or negative infinity. Okay. Now a horizontal asymptote, as you can imagine, is similar. And here's an example of a horizontal asymptote. This might be this dotted line, and if this is also 2, we would call this horizontal asymptote here x equals 2 if the graph, and they can do different things, but one graph might do something like this. And you can see that in this example, it's a very sloppy example, but the graph can cross over a horizontal asymptote. It doesn't often, a lot of times it doesn't. It can cross over the horizontal asymptote, but it will settle back in right next to that horizontal asymptote as the graph goes off to infinity, right? So a more formal definition here says a horizontal line y equals b is a horizontal asymptote if the graph approaches the line as the inputs get large. So we might say as x approaches positive or negative infinity, f of x would approach that value of b. Oops, I made a mistake. I wrote x equals 2 there. That isn't x, is it? That's y. There, y equals 2. Okay, let's look at an example. Here's a graph. This one's a little more interesting than those that I just drew. Okay, and I'm going to put some arrows on here to indicate that graph goes on to infinities. So glancing at this graph, can you see, does it have any vertical or horizontal asymptotes? Well, sometimes vertical asymptotes are easier to see. It looks like we have 2. I see one right here. And again, that's an invisible line, or a line that the graph would not cross over, right? And that one, that's a -1 there. That one is occurring at x equals -1. I see another one here. That's a 2, so that one is occurring at x equals 2. Now, do we have a horizontal? It looks to me like we do. It looks to me like we have a horizontal asymptote right here. Right here, that's also a 2, at y equals 2. Okay. All right, how do we find asymptotes? Well, let's start with vertical asymptotes. If we have an equation, we can find vertical asymptotes. Vertical asymptotes are going to occur where at values that cause the denominator to be 0, but the numerator to not be 0. Right? If we have a value that causes both the numerator and the denominator to be 0, then we would say that there is a hole in the graph. There would be a hole in the graph there, right? So, for example, if the graph was, I don't know, maybe, let's put a little sketch on here. maybe something like this. Real simple one. Okay, look, there's two zeros there. There would be a hole in the graph. You would indicate it with an open circle somewhere on the graph, right? And that's what we would call a hole in the graph. All the values close to that would be okay from either side, but at a particular value here, and we'll just say it's, I don't know, 5, 2, that particular value at 5, 2 would be considered a hole in the graph. Okay, so we usually like to think of rational functions in their factored form, because then it's easy to find values that make the denominator 0. Let's look at some examples. All right, so f of x is 5 over x plus 1 squared. That one's already factored. That's kind of nice. Then the denominator is just a factor of x plus 1 with a multiplicity of 2. All right, so what value would make the denominator 0? Well, we would just want to set that factor equal to 0 and solve, right? So we would just subtract 1 from both sides, and we see that when x is equal to -1, the denominator is 0. So that means we have a vertical asymptote at x equals -1. Okay, look at part B here. Now this one does not have a factored denominator, does it? Well, let's see if we can factor it. If we can factor it, that's going to be much easier, because to find the vertical asymptote, we have to set that denominator equal to 0 and solve. Let's see, I think that one does factor. Yeah, that's going to factor into 2x plus 1 times x plus 3. Yeah, okay, so let's rewrite that in its factored form. That numerator already is factored, right? That's 5 minus x. The denominator is 2x plus 1 times x plus 3. All right, so I have two factors of the denominator. Let's see where those vertical asymptotes are. Since there's two factors, I'm going to have two vertical asymptotes. Okay, the first is going to occur when 2x plus 1 equals 0. Solving for x, we see that we have a vertical asymptote at x equals -1/2. Right, so there's our first one. We have another one because then we have a second factor there when x plus 3 equals 0. Solving for x there, we can see that x equals -3 is our second vertical asymptote. Okay, so again, finding vertical asymptotes means setting the denominator equal to 0 and solving, and that's where vertical asymptotes will be. Now, remember that we can have a hole in the graph. The hole in the graph will occur for any value that makes both the numerator and the denominator equal to 0. Right? Neither -3 or -1/2 makes that numerator 0. So this g of x does not have a hole anywhere, right? Those are just asymptotes. Let's look now at h of x. Let's see, both the numerator and the denominator here can be factored, can't they? Let's see, that numerator is going to factor into x minus 3 times x plus 2. Then that denominator is going to factor into x minus 2 times x plus 2. All right. So again, we do have two factors in the denominator, which could lead us to two vertical asymptotes. But look at this factor x plus 2. It's also in the numerator, right? So if we set x plus 2 equal to 0 and solved, we would say there would be a vertical asymptote at x equals -2. However, the value of -2 makes that numerator equal to 0. So that's not going to be an asymptote. That's going to be a hole in the graph. An easy way to find these is you will have factors that divide out. If the factors divide out, that's indicating there's a hole in the graph, and that's right where it is. All right, so this graph has a hole at x equals -2. All right, there's a vertical asymptote though. Also, there's a vertical asymptote at the value where x minus 2 equals 0. And of course, that's x equal 2. All right? So again, values that cause the denominator to be 0 are vertical asymptotes, right? Because that can never occur. It makes sense, right? Think about it. Can you divide by 0? No. So that value, whatever value it is that makes that denominator 0, cannot be part of the graph. It cannot be there. Okay. Now, horizontal asymptotes are a little bit more interesting. Okay, to find the horizontal asymptote, we have to look at the degree of the numerator and the degree of the denominator. That's what will lead us to finding the horizontal asymptotes. All right, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Let's do this. Let's see if I can summarize something. Let's say the degree of the numerator is n. Oops. And we'll let m, I guess, be the degree of the denominator. All right. So what this is saying here is if n is greater than m, there's no horizontal asymptote. Does not exist. There just isn't one. All right. But if the degree of the numerator is less than the degree of the denominator, there's going to be a horizontal asymptote at y equals 0. Right. So if n is less than m, the horizontal asymptote is going to be y equals 0. Now, lastly, if the degree of the numerator is equal to the degree of the denominator, then there will be a horizontal asymptote at the ratio of the leading coefficients. So this is interesting. So if n equals m, right, the horizontal asymptote, it's going to be the leading coefficient of the numerator, maybe call that a sub n, over the leading coefficient of the denominator. I don't know, maybe call that a sub n, right? Of course, it's an equation, so y equals. Let's look at some examples of that. All right, so here we have some rational functions. Let's find the horizontal asymptotes. So we need to investigate the degree of the numerator and the degree of the denominator. In f of x, the degree of the numerator is 2. The degree of the denominator is also 2, right? So n equals m here. The degrees are the same. We now then need to make a ratio of the leading coefficients, 2/3. So our horizontal asymptote is going to occur at y equals 2/3. Okay, look at g of x. Here, the degree of the numerator is greater than the degree of the denominator. So n is greater than m. What does this tell us about the horizontal asymptote? This tells us that there is no horizontal asymptote. One second here. Okay, here's how I remember this. I could do long division on this. And since I can, there's no horizontal asymptote. All right, and then C, we look at the degree of the numerator and the denominator. And here we see that the degree of the numerator is less than the degree of the denominator. Okay, so this tells us that there will be a horizontal asymptote at y equals 0. The horizontal axis is always going to be the horizontal asymptote when the degree of the numerator is less than the degree of the denominator. Okay? All right. So there's one other type of asymptote I want to talk to you about, and that's the oblique asymptotes. All right. An oblique asymptote is sometimes called a slant asymptote. It's an asymptote that has the equation of a line that has a slope as well as a or usually a y-intercept to it. Okay, these oblique asymptotes, they occur when the degree of the numerator is 1 larger than the degree of the denominator. Right? So let's think about that. The degree of the numerator, that would be the n. When the degree of the numerator is 1 larger than the denominator. If we wanted to write a little note for that, we could say that n equals m plus 1. All right. To find the equation of the line for that oblique asymptote, right, we're going to perform long division on the polynomials. Okay, that will divide the numerator by the denominator. The quotient that's left after we do that long division, it's going to be a linear function, right? Or it's going to be a line at mx plus b, right? That line is going to be the oblique asymptote. All right, let's look at an example of that. Okay, so in f of x, let's see if we can find the oblique asymptote. Well, we can see the degree of the numerator is 2, the degree of the denominator is 1, right? So n is equal to m plus 1. The degree of the denominator is 1 less than the degree of the numerator. So we want to do long division. We want to do long division then to find the oblique asymptote. All right, so let's set that up. We'll do our long division maybe right here. We'll divide that by x minus 1. X goes into 2x squared 2x times. When we multiply that out, we have 2x times x is 2x squared. And 2x times negative 1 is negative 2x. Let's subtract that. All right, 3x minus negative 2x, that's 3x plus 2x, or 5x. We're going to bring down that negative 8. X goes into 5x minus 8 5 times, positive 5 times. Okay, and this does not evenly divide. Is that going to matter? We have a remainder here of negative 3. It does not matter. We don't care at all about the remainders. All we care about here is the quotient. So this oblique asymptote is going to occur at y equals 2x plus 5. Let's try one more. Here, the degree of the numerator is 3, the degree of the denominator is 2. However, it's still 1 more than the degree of the denominator, so we should be able to do long division on that and end up with a line, or the variable will only have degree 1, right? So let's try that. We are now going to divide 2x cubed plus x squared plus x by x squared plus x plus 1. All right, now x squared goes into 2x cubed. X squared goes into 2x cubed, 2x times. Okay, so let me put that goes over here in the x column. All right, so 2x times x squared is 2x cubed. 2x times x is 2x squared. And 2x times 1 is 2x. All right, let's subtract that out. X squared minus 2x squared is negative 3x. No, I'm sorry, it isn't. It's just negative x squared. I don't know why I did that. All right, and then x minus 2x is another negative x. All right, so there's no constant here, but I could say plus 0, right, and bring down that 0, which is kind of silly, but I could think about it that way. And let's keep dividing. How many times does x squared go into negative x squared? It goes into there negative 1 time. And the negative 1 times x, of course, is negative x, and negative 1 times 1 is negative 1. When we subtract that out, we're just left with 1. We don't care about the remainder. We only care about the quotient. So our oblique asymptote then is going to occur at y equals 2x minus 1. Excuse me. Okay, so vertical asymptotes are found by setting the denominator equal to 0 and solving. All the solutions will be vertical asymptotes unless one of those solutions results in a 0 denominator. Another way to think about that is that one of the factors divides out. If a factor divides out, that's a hole in the graph, right? Horizontal asymptotes are found by comparing the degree of the numerator to the degree of the denominator. All right, when the degree of the numerator is less than the degree of the denominator, there will be a horizontal asymptote at y equals 0. When they're the same, you make a ratio out of the leading coefficients, and that will be your horizontal asymptote. When the degree of the numerator is 1 more than the degree of the denominator, you will have an oblique asymptote. But you will have no horizontal asymptotes, right? There won't be any when the degree of the numerator is greater than the degree of the denominator. All right, let's see. All right, let's kind of pull all this together and let's take a look at a couple of examples of finding all of the asymptotes of a function. All right, so f of x is already factored for us. That's very nice. Do any of these factors divide out? No, so that tells us there's no holes. All right, let's start with the vertical asymptotes then. They are the easiest, I think. Well, maybe not, but let's just find them anyway. We'll start with the vertical asymptotes. So the vertical asymptotes occur when x minus 1 equals 0. So x equals 1. There's one vertical asymptote. We have another one that happens when x plus 1 equals 0. So x equals negative 1 is our second vertical asymptote. All right, for the horizontal asymptotes, we have to look at the degree of the numerator compared to the degree of the denominator. Right? So the degree of the numerator here, if we multiplied all that out, it'd be x times x, we would have x squared, right? Or just add up the exponents on the variable to know the degree of the numerator. So the degree of the numerator is 2. The denominator, however, look, this is x minus 1 squared. So the degree of the denominator is going to be 3. Right? Since the degree of the numerator is greater than the degree of the denominator, then we know there is a horizontal asymptote, and it is the horizontal axis, or the line y equals 0. And again, that's simply because the degree of the numerator is less than the degree of the denominator. Okay, let's look at the next example. In the next example, well, I don't really know. I think I might need to see if this factors to see if it divides out and it's a whole, that x minus 5. That might lead us to a vertical asymptote, but I should check. Let's see. I don't think it will. Let's see. 5 to 50. No, that doesn't. So that's not going to be a hole in the graph. So then we know we have a vertical asymptote when x minus 5 equals 0, or when x equals 5. All right, now for the horizontal asymptote, we'll compare the degree of the numerator to the degree of the denominator. So its degree of the numerator is 2. The degree of the denominator is just 1. So what does that tell us about horizontal asymptotes? That there's none, right? But since the degree of the numerator is 1 more than the degree of the denominator, that tells us that there's an oblique or a slant asymptote. So we can find this oblique asymptote with long division. Let's go ahead and do that. We're going to divide x minus 5 into 2x squared minus 3x minus 20. Okay, x goes into 2x squared, 2x times, and we multiply that out and subtract. 3x plus 10, negative 3x plus 10x is going to be 7x. And let's bring down that negative 20. X goes into there 7 times. Okay, we have a remainder, but we don't care about that. There's our oblique asymptote. Our oblique or slant asymptote is y equals 2x plus 7. Okay. All right, let's talk for a minute about the intercepts of rational functions. Right? They're found in the same manner that we find the intercepts of any other function, right? To find the vertical intercept, right? To find the vertical intercept or the y-intercept, we just let x equal 0. So we're just going to let x equal 0 and solve. So really what we're doing is we're just evaluating f of 0. All right, well, where's that intercept going to be? Let's see, the numerator is going to be 0 plus 2 squared. That's 2 squared, or 4, times negative 3. So that numerator will be negative 12. The denominator is going to be 5 times 3, 15 times negative 1, negative 15. Okay, let's reduce that since we can. That will reduce down to 4/5. All right, so we know that we have a vertical intercept at 0 4/5. Okay, there's our vertical intercept. Now, to find the horizontal intercept, we're going to do it the way we do with all other functions. Except it's easy. We can kind of forget about the denominator, right? Because to find the horizontal intercept, we let y, or f of x, equal 0 and solve for x, right? Well, if f of x equals 0, right, if f of x equals 0, look what I'm doing. I'm saying 0 equals all of this. The first thing I would do would be multiply to get that denominator gone. Well, 0 times the denominator is still 0, right? So we don't even care about that denominator there. All we have to look at is the numerator, right? So we just want to solve 0 equals x plus 2 squared times x minus 3. Again, we don't care about that denominator because look what's going to happen. It's x plus 5 times x plus 3 times x minus 1. The reason we don't care about it, because solving this equation, the first thing that we would do, right, is multiply both sides by the denominator to clear it, and then it just goes away. Both sides, let's see, x plus da, right? X plus 5 times x plus 3 times x minus 1. Look, they divide out, but 0 times all of that is still just 0. So all we ever care about is the numerator and setting that numerator equal to 0 and solving. All right, this one is factored, so we can use the zero product principle, which makes it easier. We're going to say either x plus 2 equals 0, and it doesn't matter that it's a multiplicity of 2, right? That's not going to affect anything here. So x equals negative 2. So one horizontal intercept will occur at -2, 0. The other one, let's look at the other factor, x minus 3 equals 0. So the other horizontal intercept occurs when x equals 3, right? Or at 0.30. All right, so to find your vertical or your y-intercept, just plug 0 in for x and simplify. To find your horizontal intercept, all we care about is the numerator. Set it equal to 0 and solve for x. All right, let's look at another example here, or let's summarize some things. If we're going to be graphing rational functions, right, we've learned several things here. First, we just learned that the numerator will lead us to the horizontal intercepts, right? All I have to do is set that numerator equal to 0, and solve, and I have my horizontal intercepts, right? The denominator leads us to our vertical asymptotes, right? So the denominator equal to 0 and solve, and that tells us where our vertical asymptotes are going to be. We can also find our vertical intercept, right, by letting x equal 0. Now, we can find our horizontal asymptotes by looking at the degree of the numerator and the degree of the denominator, okay? And then when the degree of a factor in the denominator is odd, okay, the function values go to positive infinity on one side of the asymptote and negative on the other side. Or look at this example here. When the degree on the factor that leads to the vertical asymptote is odd, the graph goes off into opposite directions. Okay? It's just like, I remember this because it's the same thing that happens with odd degree power functions, right? The power functions, it's the end behavior though. With rational functions, when the degree of the factor that leads to the asymptote is odd, so 1, 3, 5, 7, the graph goes in opposite directions to opposite infinities. However, when the degree of the factor in the denominator is even, then you'll see that the function goes off to the same direction. Both go to infinity or they both go to negative infinity, like here. So this first example is an odd degree factor, or the multiplicity is odd on the factor that leads to this. First one. And the second one over here has an even degree factor, like maybe 2 or 4. Okay, now let's look at an example with some of that new information. Here's this. Here's a graph in orange, and it should have some arrows. It does go on. When we look at this graph, we can notice some things, right? What can we notice about this graph? Well, we can easily find our vertical intercepts, right? Because we have a factored denominator, vertical intercepts. I'm sorry, vertical asymptotes. The vertical asymptotes are going to occur at x equals 1 and x equals -3, right? We get those vertical asymptotes from the factors of the denominator. Now look, at x equals 1, that's an even degree factor that leads us to the vertical asymptote. Here's the vertical asymptote. Here's the vertical asymptote right here, x equals 1. And look at the behavior of the graph. It's going in the same direction because of the even degree on that factor. Now, at the vertical asymptote of x equals -3, that one is right here, we can see that the graph goes to opposite infinities. The graph goes off to opposite infinities because the degree, of course, is odd. It's a degree 1, which is an odd number. Okay. Does this one look like it has a horizontal asymptote? Probably, right? Can we determine it? Oh, yeah. Look, horizontal asymptote. What is that going to be? Horizontal asymptote. Well, the degree of the numerator is 3. The degree of the denominator is also 3. They're the same. So what are the ratio of the leading coefficients? It's just 1 over 1, right? So we have a horizontal asymptote at y equals 1 over 1 or y equals 1. So there's our horizontal asymptote. Visually, you can glance at it and it looks like there's one there. Now we know how to find it exactly, right? Now look, see, I mentioned that the graph could cross over the horizontal asymptote. It doesn't off to the left. Here to the right, it does. It crosses over that horizontal asymptote. That's our y equals 1, a dotted line. But look how it's coming back to it. As we follow this out towards infinity, this graph will come closer and closer to this horizontal asymptote. It will hug that asymptote. All right, and of course we have some zeros. Here's a zero of the function when x equals -1. When x equals -1, y is going to be 0, right? Let's see. If we were to find that, what would we do? Set the numerator equal to 0 and solve. Oh, wait, I'm sorry. I said that backwards. That's not right. Oh, yeah, it is. Set the numerator equal to 0 and solve. So 0 equals x minus 2 squared times x plus 1. All right, so for our horizontal intercepts, right, either x equals -1 or x equals 2. Okay, so we've got one at 2, 0, and we've got another one at -1, 0. So the degree on the factor that led to that 0 is 1. It's odd. And look at what the graph does at that 0. Crosses right straight over. That's what degree 1 polynomials do at their horizontal intercepts. Remember that? And then look for at the intercept of x equals 2. Over here, look, the graph comes and approaches and it intersects, or intercepts, I should say, the axis, but then it bounces right back off again and comes up. And that's the behavior of the factor that leads to 0 with an even degree or even multiplicity. It bounces right off. Okay, let's look at another example. Let's see if we can sketch the graph of a polynomial function based on what we know about it. Okay, now I'm not going to just pick x values, find y values, and try to figure out what this graph does. Sorry, polynomial. I said polynomial function. I meant rational function. The graphs of rational functions can be complex. They can be pretty complicated, asymptotes and everything else. So the best way to sketch a graph of a rational function, this is graphing rational expressions. It should say functions because it's not an expression, right? It's a function. All right, so the best way to do that is to use these characteristics we've just discussed. Where do we begin? It doesn't really matter. How about if we start with the vertical asymptotes? Okay, let's look at that denominator. We have a factor of x minus 1. That means x equals 1 is one vertical asymptote. We also have a factor of x minus 3. So that means x equals 3 is a second vertical asymptote. So I'd go ahead and sketch those right onto my graph. There's x equals 1. And there's x equals 3. This is a very good starting point for us, right? We know the vertical asymptotes. While we're at it, should we go ahead and find the horizontal asymptote, if there is one, or oblique? Let's take a look for a horizontal asymptote. What's the degree of the numerator? Well, this one's a 2. There's a 1 on that guy. Well, I guess it would be out there. So the degree of the numerator is 3. What about the denominator? Looks like the degree of the denominator is the same. So that tells us, right? Oops, this must be an M. That tells us, since n equals m, that we have a horizontal asymptote at the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator, right? Or at y equals, maybe we might do it like this, a sub n over a sub m, which for this guy, the leading coefficient of the numerator is just 1. Leading coefficient of the denominator is 2. So that's telling me I have a horizontal asymptote at y equals 1/2. Okay, so I think I can put that in on my graph. There's my asymptotes. Now, what is all this graph doing? Well, let's find the intercepts next. I think that's going to tell us something. Let's do the y-intercept first. So let's find f of 0. F of 0, let's see, the numerator is going to be 0 plus 2 squared. That's going to be 4 times negative 2. So the numerator will be negative 8. All right. The denominator, let's see, that's negative 1 squared. So that's 1 times 2, that's 2 times negative 3, that's negative 6. All right. Let's see, negative 1, it's a positive 1 because it's squared, times 2. It's a positive 6, isn't it? Negative 1, 0 minus 1 is negative 1 squared, right? And that's 1 times 2 is 2 times negative 3. Okay, so it's positive 6. Or if we reduce that down, that's going to be negative 4/3. All right, so where is that at? Let's see. Negative 4/3. It's about here somewhere. Okay, about there somewhere. So let's see, are there horizontal intercepts? Okay, so that's our vertical intercept. Let me try writing that again. Let's try the horizontal intercept. That's going to occur, right, when the numerator is equal to 0. So 0 equals x plus 2 squared times x minus 2. Solving, since it's already factored, this makes it nice. Either x plus 2 equals 0 or x equals negative 2 here. If x minus 2 is 0, x equals 2. So it looks like I have 2 horizontal intercepts at negative 2 and positive 2. So there's one there, and there's one there. Oh boy, I know 3 points that are on this graph and nothing else, do I? So how can I tell what's going to happen here? How can I tell? Well, I do know these 2 points are both on the graph, right? So they're going to have to connect, sort of, right? Here's the vertical intercept that we can't cross over. So we would keep coming down like that. It's going to do something like that, right? This is a horizontal intercept just above the horizontal axis. It might cross over it, but probably wouldn't. I'd probably just draw that one that way. So that's probably what this little portion of the graph looks like just by, using some logic on that. Now, what about this middle portion here? Well, I don't think we're really going to go up above that horizontal axis, and we can't cross the vertical axes, so this is going to have to do this, right? By logic. But what's going to happen over here to the right of x equals 3? Okay, well, take a look at the degree of the factor that led us to that vertical intercept. All right, so go back up here. X minus 3, that's an odd degree on that factor, right? Compared to x minus 1, an even degree. Look at the vertical intercept at x equals 1. Look, the graph is going in the same direction. Well, because we have an odd degree, right, on the factor of the denominator that led to the vertical asymptote of x equals 3, we know that the graph has to go in the opposite direction. So it has to go up here somewhere like this, doesn't it? Since we have this horizontal asymptote that it doesn't likely cross, we can draw a pretty good sketch by saying the rest of this graph is going to do something like that. Okay. All right. So if we wanted to write the formula or the algebraic representation of a rational function, right, and we knew some things about it, or we had the graph of it, now we've learned enough that we could probably do it. A rational function, of course, is just going to take this form where the numerator is going to be factors of some polynomial. The denominator is going to be factors of some polynomial. And we can determine those factors, right, if we know the horizontal intercepts and the vertical asymptotes. And then there might be some stretch factor that we would have to put in front. We could probably use a clear point on the graph to determine that stretch factor. All right, let's look at an example. Let's see if we can figure out what this equation might be. All right, we're supposed to write an equation for a rational function. It has vertical asymptotes, right, at x equals -2 and x equals 3. So right away, vertical asymptotes starts telling me those are factors of the denominator. Let's make them factors. If the vertical asymptote is x equals -2, there's going to be a factor there of x plus 2. The vertical asymptote is x equals 3. There's going to be a factor in that denominator that's x minus 3. Okay, that's what we know that. We've seen that. That's what we've learned from that. Now, that's not telling us anything about the multiplicity of that factor, so we'll have to assume it's 1. Now, there are x-intercepts at -4, 0, and 1, 0. Okay, we know the numerator leads us to the horizontal intercepts, right? So that means we have to have a factor in the numerator of x plus 4, because that's how we would get the x-intercept of x equals -4. And then we also have a factor in there of x plus 1, because that's what would lead us to the x-intercept of 1. I'm sorry, that's a negative, x minus 1, because that's the factor that would lead us to the horizontal intercept at 1, 0. Okay, so we know a lot about this equation, right? We do. We don't know, though, if there's a stretch factor here, right? We don't know that. We could call our function f of x. And it's possible there are some multiplicity on these factors. So there's probably a number of rational functions we could write that have these characteristics, but we're going to assume the lowest, and we're going to assume there's no multiplicity on any of these factors and see if this works for us. We know we have a y-intercept at 0, 5. What is that telling us? Well, that's telling us that when x is 0, y is 5. So that means I should be able to substitute the coordinates of that point into my equation and use those to solve for a. All right, let's try that. So if y is 5, f of x would be 5. So 5 equals a times, and in my numerator, 0 plus 4 is 4. 4 times -1 is -4. 0 plus 2 is 2. 2 times -3 is -6, right? Which, of course, would reduce down to 2/3 a. Just reverse the order, all right? So to solve for a, we can just multiply both sides by 3/2, right? Because then everything divides out here, and a is going to be 15/2. Oops, 15/2. So now I can write my rational function. It's going to be 15/2, or 15 times x plus 4 times x minus 1 divided by 2 times x plus 2 times x minus 3. Okay? Let's do one more example. Let's just look at this graph and see if we can write the equation that would give us this graph. All right, so what are we noting here? I see two vertical asymptotes, right? One at x equals -2. Let's start with those. And another one at x equals 4. That's going to tell me two factors of the denominator, isn't it? X plus 2 and x minus 4. Now, what about the multiplicity of those factors? Since we've got the graph, we can determine the multiplicity. Look, at x equals -2, the graph goes in opposite directions. Right? So I'm going to assume the smallest multiplicity. I'm going to say the x plus 2 is just to the first power. Then look over here at the x equals 4 asymptote. The graph goes off to the same direction. See that? Same direction. So that tells me the multiplicity on the factor that leads to that asymptote has to be even. So I will assume the smallest, and I'll say it's 2. Okay, that's cool. We got a denominator. Now what about the numerator? Remember the numerator, the numerator leads to the zeros of the function, right? Or the horizontal intercept, and I see one right here. I see one right there at the coordinate 2, 0, right? So that's telling me I have a factor in the numerator, right? A factor in the numerator of x minus 2. Now, what's the multiplicity on that factor? Well, look, the graph comes down here, and it touches and bounces off, right? So it looks to me that that intercept has to have an even multiplicity. So I'll just assume the smallest and call it 2. Okay. Now I also can see my vertical asymptote looks like that's right at 1/2, doesn't it? It looks like the vertical asymptote is 0, 1/2, right? So that's going to help us to determine our search factor. Okay, let's see, if it's 0, 1/2, I have these x and these y coordinates, that would mean that 1/2 has to equal a times 0 minus 2 squared. Let's see, that's going to be 4 over 0 plus 2, or 2 times negative 4 squared, that's 16. 2 times 16, 32. Right? Of course, that'll reduce down to a times 1/8. Right? So if I multiply both sides by 8, they'll solve for a. Right? So it looks like a is 4. Now I can write my full function here. F of x equals 4 times x minus 2 squared over x plus 2 times x minus 4 squared. Right? And that ends the lecture for section 3.7.